this is the Faster Pwning Assured talk, Hardware Hacks and Cracks with FPGAs. We did our best to try to integrate FPGA into the title of the talk. My name is Dan Moniz. This is David Hulton.
Hey.
We're talking mostly about a series of collected, essentially FPGA projects that each of us has been working on. And for the rest of the talk, what you'll sort of see the trend being is that although I'm wearing the jacket, David represents the high end of FPGA hacking, and I represent the ghetto end of FPGA hacking. This monstrous green beast of a machine over here, which David will talk more in detail about, is David's. This teeny little green beast is mine. So we'll talk more about it in detail in a little bit, but that's like just so you have the idea of what we're going to be going into. So we get into a quick introduction into FPGAs, which David's going to handle. We talk specifically in some detail about an FPGA made by Xilinx, which is one of the two major companies that make FPGAs, the other being Altera. It's the Vertex 4, which he uses every day, and which is also the made FPGA based on this machine, this green beast. Then we go into a tool called Cowpatty, which is really an FPGA project, and we have a special guest ninja who we're going to bring up on stage to talk more about that, as well as Airbase, which is another guest ninja special. And then finally, I talk about cheap crack, and we'll sort of play off each other as we go along. It is the last talk of the day, on the last day of the conference, so we're going to, woo, woohoo, woo! I wish it was a beer, but it's a Pepsi, but it's free, so I'm not complaining. So we're gonna go into the details of Cowpatty, the details of Airbase. I'm gonna talk about cheap crack, and to be fair, cheap crack is, unlike this well-produced piece of sexy hardware, cheap crack is essentially something that we're releasing actually at TourCon at the end of September, early October. This is a sneak peek for people who are interested in FPGA stuff, which is hopefully is all y'all in the room. So we're not releasing cheap crack. I'm just going to talk about it. And one of the self-serving reasons I talk about it is because it is essentially a community project, which we'd love to get other hands on and other funding for. So if people have like 10, 20 bucks to throw towards it, or want to just pimp it on a website, or just give us ideas, certainly David and probably most of y'all in the room know more about FPGAs than I do, yet I'm doing the project. So with that, let's move into it. I'll let you do this.
Oh, okay.
I'm going to drink.
So FPGAs, just as a quick intro, how many people in the audience have heard of an FPGA? And
Word.
Wow, okay. How many have actually done some cool hacking stuff on FPGAs?
Not very cool, but
Okay.
How many want to?
Awesome. Yeah, how many people want to, yeah? Woo! Yeah! So an FPGA, if you don't know what it is, but it seems like most of you do, so I'll kind of skim through this really quickly, is a collection of different types of gates, flip-flops, other components like block RAM, DSP-48s, DCMs, LUTs, all sorts of different components that you can just connect together however you want and make any sort of logic that you want. And this is actually a picture of a Vertex 4 LX25. I don't know if you can see it with the contrast on there.
Can everybody see it in the back? Is the text readable? Yeah? Okay, great.
So if you can see the blue highlighted areas, those are actually the input-output blocks where all the pins actually come into the FPGA die. And in the middle, that's where all the DCM sort of stuff, well, all of your clocks usually get routed through there, so they're right close to the DCMs and close to the middle of the FPGA, so it can route out to all of your logic. Then you have a ton of slices, which are in these rows. They're basically like the workhorse of the FPGA, where everything gets routed and done. And the LX25 has about 10,000 of those, just to give you an idea of how many different units are in there. And then there's a bunch of DCMs that let you multiply and divide clocks however you want. So if you have like a 50 megahertz clock coming in, you can multiply it up to like 300 or 500 or divide it down to whatever. And there's 8 of those on the LX25. And then there's some rows of RAM, block RAMs, which are kind of similar to like cache on your processor. With this, you get 72 of them. Each one of them is about 18 kilobits. So you get a fair amount of storage that you can just use for storing general purpose sort of stuff, whether you don't want to store in registers. And then on this particular model, there's DSP-48s in this one row along here. There's 48 of those, and you can do really high-speed multiplies. Basically, each of them you can do like up to 18 by 18 multiplies at 500 megahertz, basically. So, and you can do 48 of those in parallel. So it's actually quite a bit of power for if you're doing multiplication, and you can also chain them and do addition, things like that. Then there's this programmable routing matrix where I believe on the LX25 there's about 18 layers of just routing. And so everything is essentially kind of connected to everything else, at least somewhat directly. And so you can have something way over on one side of the FPGA that's talking to something on way on the other side, and it's just automatically routed through this huge matrix. So now DNM's going to do an intro on the WPA stuff.
So WPA, part of the project, one of the projects that David and a bunch of other super ninjas are working on is the ability to use FPGA hardware. And again, by saying FPGA hardware, I'm being slightly redundant. What I really mean here is reprogrammable hardware to accelerate the cracking of WPA keys, right? Encrypted WPA keys. And so WPA, who's familiar with WPA? Who's heard of or used WPA suite? Right, so essentially successor to WEP, right, for 802.11 networks security, right? Better network security characteristics generally than WEP, although it's hard to be worse than WEP. But having said that, no, I mean, basically, the protocol is not as breakable as easily by far. So the idea here was to build a model of WPA and then find a way, like, what are the easy ways to build essentially dedicated hardware for cheap, comparative to, and all these things you got to remember are comparative to the cost of fabricating your own ASIC, right? Your own actual chip, because FPGAs are reprogrammable. I should mention. We should show the card. So a Vertex 4, which David just went into, is about yay large. Like this is a board. The Vertex 4 is this. Yeah. Right. Pull up. So this is the whole board, and this is the Vertex 4. The silver die-looking thing, right? That's the Vertex 4. It's essentially one Vertex 4.
Yeah.
All right. On one PC card, right? Like this is essentially like a PC card form factor. And they also come in.
Yeah, the demo we're doing is actually on our compact flash cards, and so the FPGA on this is actually like much tinier. It's really tiny, and that's the LX25. And this is actually, you can get this with like over twice the amount of logic as the one for this, so this one's actually pretty decent. Yeah, right, all the demo for this is going to be done on these little cards.
Basically a huge parallel machine full of compact flash cards. But anyway, so getting back to the idea behind WPA here, the whole idea is how can we actually make, essentially a hardware-accelerated WPA cracker, right? Now, this is not a project that I worked directly on. I was sort of aware of it, and I knew people who were working on it, knew David, knew some of the other super ninjas who were involved. But this is an example of WPA. So if you're familiar with WPA, this is essentially a little review of it. But basically, the first process here is to go get the key from the authentication server, right? You get the pairwise master key, PMK. Then you do the PTK transaction, GTK. I'm blowing through all of this because really this talk is not an explication of how WPA works or doesn't work. This is a model, and the idea here is just to point out, well, what can you actually attack, right? Like, what is the threat, the attack surface or the threat model for WPA? I'll let you do this one.
Oh, okay.
We'll switch off.
Okay. So yeah, basically you type in your passphrase into your access point or into your wireless client, and it actually runs it through this pbkdf2 function that hashes it with SHA-1 a bunch of times. And then it takes that value and uses that for the actual, like generating your PTKs, your pairwise transient keys and stuff like that for the actual network authentication and for using like for all your encryption and stuff. So, come on. Yeah. So if you look at the pbkdf2 function, it actually runs pbkdf2 twice. And if you look at the code here, it's basically running SHA-1 HMAC 4,000 times, and then it does that again, and so it does tons of computing like just to create this hash, and they run it 4,000 times just so it takes forever. So if you're trying to generate these things and you're a malicious person, you can only, it's way slow doing it. So if you kind of dive a little bit further and look at the SHA-1 HMAC function, basically what it does is you take your passphrase that you type into the access point, and it gets XORed with some values, and it gets run in SHA-1 if you know what an HMAC does. And essentially, like with this inner loop here, I don't know if you can see the mouse there, the inner loop, that will end up having like the same inner state every single time you run it, because the master key never changes. And so there's like this inner kind of state, and then that gets kind of fed into the next one. It basically gets appended on when you run this outer SHA-1. And so the cool thing is that you can just cache like the immediate one here, and so it cuts down on half the amount of SHA-1s you have to do. If that makes sense. Does that make sense? Yeah? Oh yeah, the salt, yeah. So Is there salt in here?
Oh, thank you.
Oh, cool.
Do I have mic range to get off the stage? Nobody know? Huh? Probably? All right.
Yeah, so
Can you hear me?
So that's one of the optimizations that people use to try and crack this, and so that's one thing that I take into account here. Yeah, the other thing that he brought up is that there's also a salt involved. It basically takes SSID and runs it through this before this whole chaining process. So there we go. If you see here, the first SHA-1 HMAC is actually done with the master key and the SSID of the access point, and then it gets run through with where basically keeps on getting the state keeps on getting appended on with the master key, like running the SHA-1 HMAC, and so all this is dependent on the SSID. The SSID is basically the salt for the whole process. And once you can generate the PMK value, then you can essentially run it through, figure out what the network traffic should be kind of like different values in the network for the exchange, and then you just compare it to a capture that you grab of the authentication, and then you can see if basically that's the right PMK for the transaction or not. So that's essentially how the cracking stuff works. Josh Wright up here actually wrote cow patty. I think he's down in the corner maybe. Yeah? Yeah.
Stand up.
Yeah, stand up. Woo!
Stand up! Oh, come on.
So, yeah, he wrote cow patty and...
One of our super ninjas.
Yeah, super ninja. And so I just took cow patty and added in hooks for cracking it with FPGAs. So on each one of these cards in here, I'm only doing the demo with 8 cards, but this system takes like 15, and it's kind of stupid because these things are so small that, and that thing's so big. So we have to build a better backplane for it, but each one of these cards has 8 SHA-1 cores in it, and we use block RAM to basically buffer all of the words that are fed to it. So the different passphrases that we use for it, we just send it out to the block RAM, and as long as we're able to keep the buffer filled, then it keeps the pipeline all nice and clean. And so all the SHA-1 cores are utilized fully as long as there's enough bandwidth there. And it's really slow, so it's really easy to keep the buffer filled. And this is basically how it works. It's essentially a ring buffer that we're using. And so the computer goes along and it starts filling in these different slots with basically just passphrases. Well, kind of the state after when we start going into the PBKDF2 part. And so it goes along and it starts filling these things up, and once it gets to the bottom, then it fires it off and says, okay, go FPGA. The FPGA starts grabbing the stuff, yeah, starts grabbing these values out and feeding them to the SHA-1 cores, and then it'll go on to the next 8 and feed them off when those are done. And then the computer will continue to fill the buffer right behind it. So as long as you're able to fill it within 256 of wherever its pointer is, then it keeps it nice and full, and you get like full utilization of all the cores. So that's one of the little things that we do to make sure that you get maximum performance out of it. So then yeah, it goes along, and then once it reaches there, then it kind of waits until that block's done processing, and then it goes on and keeps on filling it. So some performance comparisons here. With cow patty on a PC, like on a cheap Ghetto P3, you get about maybe 25 per second.
Why are you insulting my main workstation?
Okay, on Josh's workstation, if you hack his workstation and you want to include it on your cluster node, then yeah, you're only getting 25, so it's probably not worth it. On a 3.6 gigahertz